Aircraft aren't very useful without a good, reliable engine. Today, we often take them for granted. We fly around the world in big, reliable airliners powered by big, reliable engines. These are usually turbofans, which are complex and beautiful pieces of machinery, but they can also run for thousands of hours between major servicing. Then, on the smaller side of things, your everyday general, civil and private aircraft also have incredibly reliable engines as well. These are usually piston engines or turboprops. These days, if something goes wrong, it's not usually the engine's fault. It's often the result of something like poor installation or poor maintenance or plain old human error, someone not understanding what they're doing. Engines very rarely go wrong on their own. You wouldn't get on an aircraft today that you knew had an unreliable engine. It's why building engines is now a $60 billion global industry. But at the dawn of powered flight, there was no global $60 billion aero engine industry. So how did we get the first flying machines into the air in the first place? Well, it took a lot of experimentation, a lot of patience, a fair amount of trial and error, and, the occasional explosion. Hello and welcome back. I am Christopher Rex Emerson. I like to talk about planes a lot, and today we're looking at the early development history of aero engines. Yes, I am finally delving into the many topics of aeronautical engineering, and people have been asking for this for quite a while, and I will be honest with you, I may have started drafting this video about 2 years ago and then proceeded to forget about it, but we're here now, so let's just pretend that that did not happen. So, the early developmental history of engines in aviation. How on earth do I even begin to approach this in a timely and organized manner, honestly? The timeline of development of aero engines before 1914 is as complex and as contradictory as the voting history of your local politician. Over the pioneering years of powered flight, so say roughly from 1850-ish to the mid-1910s, engineers and inventors and other gifted and mechanically crazed individuals explored numerous solutions to the same problem, or rather question. And that question is, what was the most effective power plant for a flying machine? And the reason why there were so many solutions tried was because if you're asking this question, you clearly don't know the answer. When powered flight began, engines were basically beginning at the same time, so everyone was learning as they went along. As it turned out, this was not an easy problem to solve. Building an engine for aviation, for powered flight in particular, is much, much harder than building an engine for, say, application aboard a ship or for a vehicle on land, say a car or a tank or something like that. It has to be powerful enough to get you into the air, it's got to be light enough that it doesn't impose ridiculous weight penalties on whatever flying machine you're building, and then it also has to be reliable enough to keep you in the air for more than, say, a couple of minutes. Now, for the most part, most early engines in this period were piston engines. I am aware there were experiments with rockets, and electrical motors were used. For example, the French airship La France used electric motors powered by batteries, but on the whole, the piston engine was the dominating power plant of aircraft, be it lighter than air or heavier than air, all the way up to the dawn of the jet age. As such, this video will focus just on piston engines. Rockets, electrical motors, and other stuff will be covered in another video later on down the track when I get around to it. Now, before we delve into the fun development history of early aircraft piston engines, I do want to quickly cover the basics and explain how a piston engine actually works, because not everyone may fully grasp this. Of course, if you already know this, feel free to skip ahead, or stay and feed the algorithm, I don't mind either way. At the dawn of powered flight, the only practical form of thrust generation was by using a rotating propeller or air screw. Now, to generate any meaningful amount of thrust, you would need to rotate said air screw at a high RPM. Now, for many centuries, this was pretty much impossible to achieve, and the best you could essentially do was hope to use people power, or possibly animal power. But by the middle of the 1800s, you could get a propeller to rotate at a relatively fast RPM by connecting it to a piston engine, which is also known as a reciprocating engine. This is a type of engine that uses pistons to convert high pressure and high temperature into a rotational force, which we would call torque. In it, you have the following basic components. You have a cylinder, which is basically a hollow tube. You then have a piston, which is a plug that slides inside the tube. You then also have a crankshaft, which is a spinning shaft that essentially spins freely otherwise, with an off-center attachment or a handle that you would normally call a crank pin. And then you have a connecting rod, which connects the piston to the crankshaft using the crank pin. Now, regardless of what fuel source you're using in this engine, it will follow the same basic steps to generate power. The process begins by filling the cylinder with a high-pressure gas. When this gas expands, it forces the piston from the top of the cylinder down to the bottom. This is called the power stroke. As the piston moves down, it pushes the connecting rod. Because the connecting rod is attached to the off-center crank pin on the crankshaft, it can't stay perfectly vertical. The rod moves to an oblique or a slanted angle because the crank pin is traveling in a circle while the piston is forced to move in a straight line. If the rod remained perfectly vertical, the force from the piston would push straight down into the center of the crankshaft, doing nothing. But because of the angle of the connecting rod, the force that's been generated by the piston is now being directed to one of the sides of the shaft's center. This causes the shaft to rotate, and that is how you are generating your torque force. This is the usable energy that then gets used to drive the propeller. This force is not generated evenly though. The turning effect of the shaft is at its most powerful at the exact moment that the connecting rod reaches a 90-degree angle to the crank pin. Conversely, at the top and at the very bottom of the power stroke, the rod connecting the piston head to the crankshaft is vertical and pointing straight at the center of the crankshaft. As I said before, if it's doing that, any forces currently being imposed upon it will not be transferring any rotational energy. Therefore, in these positions, there is no energy being transferred to the shaft at all. This is known as top dead center and bottom dead center, depending on the position of the piston, and depending on where you are in the world, it's probably called different things, but this is how I learned it anyway. Now, at the end of the power stroke, this piston is at the bottom of the cylinder. At this point, the pressurized gas that has expanded and pushed it down probably doesn't have much energy left in it, so it needs to be cleared out. This is done with an exhaust valve. This usually opens at the top of the cylinder, and the piston is moved back up to the top of the cylinder to push the gas out of it. But how does the piston move back up? It's now at the bottom, and that means the connecting rod is pointing straight at the center of the crankshaft, so there is going to be no power there to move the piston. Well, some of the torque energy on the rotating crankshaft is stored in a flywheel, which is basically a giant, heavy, spinning disc attached to the crankshaft itself. Think of it kind of like a spinning top. You know, if you set off a spinning top, it spins for ages and ages and ages and ages and ages, and that is because of something called inertia, or stored momentum. The stored momentum of the flywheel basically carries the crankshaft through those vertical dead center stages where the connecting rod is generating no turning power. This keeps the engine spinning through until the next power stroke is available. In a single-cylinder engine, the flywheel is absolutely critical. But what about multiple cylinder engines? Would that not get around the problem if you stagger the power strokes? Well, kind of. The power strokes of the various pistons can be timed to occur at different intervals, which means the power from the other pistons connected to the same crankshaft can then provide the force necessary to return another piston to the top of its cylinder. The flywheel in this case still has a job, and its job is to smooth out what you would call torque variation. This is basically pulses of power that is transmitted from the piston to the crankshaft created by each cylinder during its power stroke. Otherwise, in simple terms, the power going to the crankshaft will kind of be like, you know, as opposed to something a bit more smoother. Now, you do get some engines that make that weird noise, but we're going to be getting into that in another video later on. But for the purpose of aviation, you don't want an engine that goes you want something smooth, otherwise you're going to shake the whole bloody thing to pieces. Anyway, before I digress any further, that in a nutshell is how a piston engine works and how it is applied to an aircraft. Now, I'm not going to explain how this power is translated to the propeller. That's going to be done in another video where we look at things like reduction gears and all the fun witchcraft that comes with that. And I'm also not going to explain today how you start the engine, because that's getting its own video too, because that is a remarkably interesting topic, and there are some very different ways that you can start an engine, depending on the type of engine that you have as well. And yeah, I could easily do a 1-hour video on that. This video is just going to focus on the power plant itself. So with that in mind, let's actually move on to the main topic of today's video, which is the development history of these early engines. Now, some of you might think we would start by looking at the engine of the Wright brothers flyer, you know, the engine that powered the first manned heavier-than-air flight. But we're not going to be doing that. Long before the Wright brothers first flew above Kitty Hawk, engines had already powered other flying machines. Admittedly, not always successfully, but hey, you do sometimes get marks for effort. However, there were some successful powered flights before the Wright brothers. They were just lighter than air flights as opposed to heavier than air flights. You know, airships. Now, what some people might not know is that the first successful powered airship flights occurred all the way back in the middle of the 1800s. And by power of historical deduction, that must mean that the first aero engines were steam engines. And you'd be absolutely correct. So before we start looking at internal combustion engines, the rough operation of which could be summarized as suck, squeeze, bang, reject, don't use that in your Tinder bio, I beg you, we need to turn to the romantic topic of steam power, the operation of which can boil down to, and yes, that is a pun, get fuel, make fire, boil water, make superheated steam, and shove said steam into various mechanical orifice to make things move. It sounds simple today, but in the 18th century it really was a case of mechanical witchcraft for some. Now, aside from serving as the inspiration of steampunk novels for centuries to come, the greatest legacy of steam power, in the context of flight, was to highlight the critical importance of a good power-to-weight ratio. The very first manned powered flight took place on the 24th of September in 1852, and this was achieved by a French engineer by the name of Henri Giffard. Now, Henri was a very gifted man. He invented the injector, which has got all sorts of applications today, and at the time it made him a massive fortune. And like any self-respecting inventor with a massive fortune in the middle of the Industrial Revolution, he got interested in making steam engines do all sorts of interesting and new things. Specifically, he got interested in flying. Giffard had already dabbled with tethered hydrogen balloons, so this was not a new thing for him. Using that knowledge, he was able to design and construct his own airship. Its envelope contained about 88,000 cubic feet or 2,500 cubic meters of hydrogen, and he also designed the little steam engine that would power it. Now, those of us gifted with good survival instincts are probably thinking that combining a steam engine that uses fire to boil water with a giant envelope filled with incredibly explosive hydrogen gas might be a bad idea. To his credit, Henri Giffard also understood this risk, which is why his steam engine would be slung 12 meters below the envelope, with the smokestack pointing down towards the ground to try and keep the sparks as far away as possible. He also had some essentially grilled filter things on the end of the smokestack to also try and contain any embers that made it all the way out as well. So he was being vaguely safe. He utilised a single-cylinder steam engine that drove a 3.5 metre diameter propeller. For the time, his engine was quite lightweight. It weighed only about 45 kilos, but it produced a whopping 3 horsepower. Then you had to factor in that 45 kilo engine weight did not factor in the boiler, the firebox, the water, and the fuel. If you roll all of that together, you now have a total power plant weight of 250 kilos, or 1/4 of a ton, producing 3 horsepower. His airship flew for about 27 kilometers, but I don't really want to say flew because for most of it he was at the mercy of the weather. He could only control this airship if there was 0 breeze at all. You would literally need to suspend the entire weather system for this thing to really work. It would probably get moved about by the wind generated by a mildly distressed pigeon, if I'm being honest. The problem was that the power-to-weight ratio of his engine was just far too low. But that, of course, then begs the question, how low is too low? We need some sort of baseline, we need a yardstick to measure the performance of these early pioneering engines by. You know, what if the power-to-weight ratio is not too far away from what's necessary? What if it's really far away from what needs to be necessary for it? Well, I think it's time that we use a couple of good engines as a baseline, which will help us get some perspective on how underpowered some of these early power plants really were. One example we could use would be something like the Lechon 9JA, which is a 9-cylinder rotary engine from 1913. It was one of the best pre-World War engines made. It weighed about 146.5 kilos and it produced 110 horsepower. This gave it a power-to-weight ratio of 0.92 horsepower per kilo. But comparing the pioneering engines to what is a fairly refined engine seems a bit unfair. So as my main yardstick, I'm actually going to use the Antoinette 8V from 1902. This was an 8-cylinder liquid-cooled V engine, and it was the first of its kind to enter series production. It was used on a number of pioneering aircraft, but unlike the Lechon engine, it was not a dedicated aero engine. It was initially designed to be put in cars and then adapted for flight. This engine weighed 95 kilograms and produced approximately 50 horsepower, which gave it a power-to-weight ratio of 0.52 horsepower per kilo. In comparison to this, Henri Giffard's steam engine had a power-to-weight ratio of just 0.012 horsepower per kilo, or 2% of the power-to-weight ratio of the Antoinette engine, and barely more than 1% of the power-to-weight ratio of the Lechon Rotary. Clearly, steam engines had a bit to go before they were going to be useful for anything other than bobbing around in mild distress. Unfortunately, Giffard and his peers were more or less just limited by the technology of the time. You could build a powerful steam engine, or you could build a small one. You couldn't yet do both. But there would be incremental improvement over the following decades. No other full-scale airships were attempted with steam engines until the 1890s. Instead, in the intervening years, the focus would shift onto experimentation. Various test rigs were built, a lot of people built steam-powered scale models, and medium to large-sized unmanned flying machines. This did a lot to help miniaturize steam engines in this field. A notable example is from 1877, when Enrico Folanini successfully tested a steam-powered helicopter. It was the first successful flight of a helicopter, admittedly an unmanned one, but it was still the first. It sustained a 20-second flight and then completed a gentle landing. What's particularly interesting with this is it used a tiny 2-cylinder steam engine. It weighed about 6 pounds or like 2.7 kilos, and produced an itty-bitty 1/4 of a horsepower. Now, it saved a lot of weight by not including its fuel source in the power plant weight that was carried aloft. The boiler was the small steel sphere that you see slung underneath. Flame was used to heat it externally, which superheated the water into steam, which then drove the propeller blades, and it was essentially spooled up and then released. It didn't carry the flame with it, so it didn't carry the fuel source with it, which saved a lot of weight. Now, as a practical machine, it was useless, but it did prove that steam engines could be made smaller and more efficient. The next advances in steam-powered aviation would come with the use of the compound steam engine. Now, this is a type of engine where steam is expanded in 2 or more cylinders. High pressure from the boiler is first fed into a high-pressure cylinder, which performs some work, and at the end of the power stroke, the steam in that cylinder still has some energy, but this is intentional. The steam gets exhausted then into a low-pressure cylinder. This cylinder is larger because steam occupies a greater volume as its pressure drops, but there's still enough energy for another power stroke of this larger, lower pressure cylinder. Compound engines offered a number of advantages. They increased efficiency mostly by splitting the expansion over multiple cylinders. It reduced the heat loss that you would suffer in a steam engine through condensation and just basic thermodynamics. It also reduced weight. Because the highest pressure was now confined to a smaller first cylinder, only that part of the engine needed to be built to withstand such strains. The rest of the engine components could be built lighter and thinner, including the lower pressure cylinder. So that meant for any given maximum pressure, a compound steam engine was lighter than a single cylinder steam engine. Though invented at the start of the 1800s, the compound steam engine was more complex and physically larger, though it was a lot more efficient. This meant it would take a lot longer to successfully miniaturize to a point where it was actually useful. But, finally, towards the end of the 1800s, the compound steam engines were small enough, efficient enough, and powerful enough to be considered potentially useful for even heavier than air flight. This led to many more steampunk-inspiring machines, often built by men with outrageous moustaches, and although today the concept might sound a bit laughable, it was at the time taken very seriously. A great example of a very efficient steam engine from the time was the one built by Clement Ader. Now, I've already covered this in a video, but I wanted to mention it here as well. So this steam engine was used to power 2 different flying machines, the Aero and then the Aviation 3. The Aero managed a small, completely uncontrolled hop, which is basically a nice way of saying it flew for about 30 or 40 meters at a height of half a meter, but it was still better than nothing because the Aviation 3 supposedly never flew at all. The engine was the true success story here. The Aviation 3 used 2 of these engines driving a pair of propellers. This power plant was a masterpiece in weight savings. The engines themselves weighed a total of just 42 kilos. The firebox and the boiler only weighed 60 kilos, and the steam condenser just 15 kilos. Combined, they generated 40 horsepower, which means, with a bit of math, we can see that that would have a power-to-weight ratio of 0.34 horsepower per kilo. This is a much more efficient steam engine. It was 28 times the power-to-weight ratio of that used in Henri Giffard's steam-powered Airship. Indeed, if we look forward into history, it actually has almost double the power-to-weight ratio of the engine that would be used to power the first Wright Flyer, an engine which I will get to later on. So yeah, Clement Ader's steam engine was nothing to sniff at. I mean, the flying machines themselves were hopeless, but the engine, that was a real and genuine improvement. Steam power was potentially going somewhere. And another great example of a steam engine used from this period and used in a flying machine was that designed by Sir Hiram Maxim. Yes, the man who gave us the Maxim machine gun was also dabbling in aeronautics. Maxim started building a flying machine in 1889. It was unveiled at Baldwin's Park in Kent, and holy cow, this thing was a monster. He built a massive biplane that had a wing area of almost 5,000 square feet. Calling it a flying machine, though, is a bit of a stretch. It was more akin to a test bed. He did not want this thing, initially at least, to fly, and it was attached to an 1,800-foot-long, 9-foot-wide railway track and held down with restraints. Like Clément Adaire's flying machines, this thing was completely mad, and the only real silver lining here is once again a truly magnificent and efficient power plant. Like the Avion 3, Maxim's flying machine was also powered by a pair of compound steam engines. These generated an astonishing 180 horsepower each, and they only had a dry weight of 141 kilos. Admittedly, this weight does not include the combined boiler and feed water heater, which added a lot of weight, but at the end it still had a power-to-weight ratio of 0.31 horsepower per kilo, which is only a little bit worse than Clément Adaire's engine, but it was still much more powerful overall. This power was used to drive a pair of equally massive propellers, which had a diameter of something like 17 feet or 5 meters. It reportedly, according to a couple of different vintage magazines from the time that I've looked through, generated a thrust equivalent of around 2,100 pounds of thrust. This was, apparently, enough to work, because when Maxim tested this giant monstrosity, it actually tried to take off. It physically lifted off from the tracks, but because it was held down by its restraints, it immediately crashed. Maxim survived unhurt, though he never made any other attempts to do this again, not necessarily because he was traumatized, but because he gave up and saw that other people were doing a much better job at this point, and admittedly he only had a very rudimentary understanding of the actual way that aeronautics works. His writings on lifting surfaces are interesting. He's a gifted inventor, but he did not understand how an aerofoil worked at all. But with a few exceptions, which I'll cover in another video later, this was the last serious attempt to make a flying machine with steam power. By this point, the internal combustion engine had well and truly arrived on the scene. Steam engines used external combustion. The fuel source is ignited outside the engine, the boiler, to generate a high-pressure gas in the form of steam. An internal combustion engine, as the name might suggest, generates its pressure by the ignition of a fuel and air mixture inside the cylinder. And in most engines, this mixture is compressed beforehand to maximize the effect of the expanding gas upon the cylinder head. As you no longer need a big, heavy boiler and big, heavy oil to generate high-pressure steam, the internal combustion engine reduces the total weight of the power plant dramatically. While advanced steam engines did achieve some truly remarkable bare engine power-to-weight ratios, they could not compete with this. The internal combustion engine quickly became the dominant power plant because the total steam installation was ultimately just too heavy and inefficient to be practical for any kind of long-distance flying. Like the early steam engine, the early internal combustion engine would also struggle with low power and poor efficiency. There's actually a bit of an overlap where both types of engines were equally unsuitable for powered flight in the latter half of the 1800s. Be that as it may, the first powered flight using an internal combustion engine took place in 1872. This was completed by a German engineer, the first of many that we're going to hear about over the next 20 or so minutes, by the name of Paul Heinlein. His airship was inflated using coal seam gas, and the engine powering it was something called a Lenoir engine. This was the first commercially successful internal combustion engine, and it was patented by Frenchman Etienne Lenoir in 1860. But it's not the sort of engine we would be familiar with today. It was essentially a repurposed steam engine. It had a double-acting layout, which meant it had a power stroke that occurred at each end of the cylinder. However, it didn't compress the air-fuel mixture before igniting it. The piston simply sucked in a mixture of cold seam gas and air into the cylinder, and it was immediately ignited, causing the gas to expand that way. Now, the engine in Heinlein's Airship had 4 cylinders, and it delivered approximately 6 horsepower. Now, if that doesn't sound like a lot of power, you would be correct. This engine was incredibly fuel inefficient, and the Airship didn't have very good range considering it consumed its own lifting gas as a fuel source at a rate of 250 cubic feet of gas per hour. Thankfully for the world of aeronautics, self-cannibalizing airships were soon to be a thing of the past, as real improvements came to the internal combustion engine in 1876. In that year, the German engineer Nikolaus Otto built and ran the first successful 4-stroke internal combustion engine. This engine operated by sucking in a mixture of fuel and air, compressing it, igniting it to move the piston and create power, and then pushing out the exhaust. Suck, squeeze, bang, eject, as I said earlier. Nikolaus would be immortalized by his own success, as all 4-stroke internal combustion engines these days are known by their operation cycle, otherwise known as an Otto cycle engine. Otto's first engine used coal seam gas, like the Lenoir engine in Heinlein's Airship, but later derivatives quickly moved on to fun, volatile hydrocarbon liquids. Some early derivatives of his engines were soon running on something called Le Groin, also known as heavy naphtha, and very soon people were experimenting with using this useless waste product from kerosene production called gasoline, but surely that won't go anywhere, would it? As it turned out, it did go somewhere. It offered better combustion rates, it offered lower operating pressures, and this meant that engines could be made much lighter. This not only promised higher power, but much higher RPMs as well. The first Otto engine to fly would be built by Gottlieb Daimler and Wilhelm Maybach. These are names that you might recognize, as they are somewhat understandably famous, owing to them being household names in the automotive industry. This is further understandable, as pretty much every early Otto engine was built with land-based use in mind, specifically with vehicles. This particular engine powered an airship that was built by another German engineer, Hermann Wolfert, in 1888. Unfortunately, I haven't been able to find a single photo of this airship, so please enjoy this wondrous photo of Wolfert in 1885, sitting aboard a test gondola for the airship he was in the process of designing and building with Daimler. His engine was based on an engine that was known as the Grandfather Clock. It was a significant development as it was the first Otto cycle engine that was developed for use in vehicles rather than as a static power engine. It originally ran at 600 RPMs, which was a significant improvement over previous combustion engines, which were only running of between 150 up to maybe 240 at an absolute stretch. While many designs would soon vary, particularly in cylinder arrangement, most Otto engines of the pioneering era of flight shared several basic components, most of which could be found on this early Daimler engine. With that in mind, I just want to quickly explain some of the core components and systems of the Otto cycle engine, as understanding them is very relevant to understanding the development of early aero engines, as the incremental improvements of these various components and systems had huge knock-on effects moving forward. The easiest way to understand how an Otto cycle engine works is to understand that it is an air-breathing engine. Like you and me, if it can't breathe properly, it won't work properly. Because of that, some of the most vital components of an air-breathing engine are either related to the air intake system or the air exhaust system. There are 2 other components I'm going to briefly cover as well, though, that aren't directly related to those systems, and that is the crankcase and the ignition. We'll start with the crankcase. This is often underappreciated when it comes to the early development of aero engines, but let me explain. The crankcase is the foundation of your engine. It's the structural support of the cylinders. It's a frame that carries the crankshaft bearings. It often contains critical engine lubrications, and it provides a mounting point to attach your engine to your airframe. The crankcase is often the largest component in an engine, be it assembled out of one solid piece or out of a few. It's essentially a giant protective shell. Because of that, and because of its functional needs, it has to be built to be incredibly durable, and this means that the crankcase is very, very heavy. Because of this, the easiest way to get some easy weight saving and to therefore increase the power to weight ratio of your engine was to design your crankcase to be as light as possible. And that led to a lot of people getting very interested in advanced metallurgy so that people could very quickly move away from the heavy cast iron crankcases that dominated early aero engines. Okay, so moving on to the intake system, the part that lets the engine breathe in, you have three major components, although there are some others in there as well. You've got the air inlet, you've got the carburetor, and you have the intake valve. Now, the air inlet was not a very specialized component at first. It was basically just a pipe that ran to the cylinder. If there was more than one cylinder in your engine, this pipe was connected to an intake manifold, which split the pipe into lots of individual pipes, one going into each cylinder. Later on, a lot more attention would be placed on the air inlet, as with the more air an engine can breathe, the more fuel you can mix with that air, which means you can get more power. But these early engines were so primitive, and limited by so many other things, and combined with a limited understanding of the mass airflow requirements of engines, there wasn't really any need or inclination to develop anything beyond a short pipe sticking out the front or the back or the side or wherever they decided to shove it. Conversely, at the beginning of things, a lot of attention and effort was put into perfecting the carburetor. With a few notable exceptions, almost all early aero engines would use a carburetor over a fuel injector as a means of mixing the fuel with the air going into the cylinders. At the very beginning, there were a lot of different carburetors being trialed by different people all over the world, but they all soon coalesced to one common design, so I'm just going to use that now, and that was the float carburetor. This essentially had two sections. You had the float fuel chamber and you had the venturi. Now, the venturi is essentially a necked down or a narrowed section of the pipe connected to the air inlet. Now, when the engine is running and breathing in, it sucks in this air and it has to pass through the venturi where you have this narrow constriction. This increases the speed of the airflow, but as airflow increases, it reduces in pressure. This creates a partial vacuum. Fuel is fed into the airflow by a small tube that is often called a fuel jet. This connects the fuel chamber to the section of the venturi where the pressure is lowest, where the vacuum is strongest. The low pressure of the venturi sucks the fuel through this narrow passage into the rushing airstream, which distributes it as a fine atomized mist. The fuel chamber is fed from a main fuel tank, of which we will get into in another video, but it is always kept full because it uses something called a float valve. The design might differ slightly depending on the individual carburetor or engine type, but the overall concept is pretty much the same. Fuel gets fed into the chamber from the fuel tank by a narrow inlet. That inlet is blocked by a pin, and that pin is attached to a float, which is floating on the fuel already in the chamber. As the fuel is consumed by the engine, the float drops down, and that pulls the pin out of the fuel inlet, allowing more fuel to come in. As fuel is used up by the engine, the float drops, the valve opens, the fuel flows in, the float rises back up, and the valve is closed. It was a very simple and very effective design, and the most attractive feature of it was the fact that it was self-regulating. The faster the engine is running, the more air would be passing through the venturi. That would make the vacuum stronger, which would suck in more fuel, which would activate the use of the float valve, and it would just keep refilling until you ran out of fuel, but that's a different problem for later. There is also the throttle to consider, which is essentially a rotating valve that controls how much of the fuel-air mix gets absorbed into the engine. But as a lot of the early aero engines that I'm discussing today had no throttle, for reasons we will be getting into quite soon, I'm going to leave that for another video that looks at slightly more advanced engines later on. The final critical intake component I want to talk about is the intake valve. This controlled when the fuel air mix could enter the engine cylinder. Most early engines used an automatic intake valve. Normally, this valve is held shut using some light springs. It is opened when the engine has finished its exhaust cycle and is going into its intake stroke. As the cylinder begins to move back down on the intake stroke, there is a vacuum that gets created in the cylinder as the gas from the preceding power stroke has already been exhausted out. This vacuum pulls open the valve because the springs holding it shut are quite light and they're configured to let it open at a particular negative pressure. When the valve opens, that lets the fuel air charge into the cylinder. Ignition of the fuel and air mixture sounds fairly straightforward, but it's actually something that went through a few changes over the following decades, beginning from around 1895. These days, when we think of ignition, we of course all probably think of the spark plug. But early electric ignitions in the first Otto engines were incredibly unreliable, for reasons that I will get to in another video. A lot of the early engines, including the early Daimler engines, used something called hot tube ignition. This system utilized either a small metal or a ceramic tube that protruded into the cylinder and was kept red hot by an external burner. It wasn't very efficient and it added a fair amount of weight, but it did guarantee ignition by the dint of it being a red hot thing in a cylinder full of air and fuel, so there is that. After ignition and the power stroke, we then get to the exhaust system, which is the engine breathing out. First, of course, you have the exhaust valve, which, like the intake valve, controls when the exhaust gases are allowed to exit the cylinder. Now, unlike the intake valves, the exhaust valve could not be an automatic system. The high pressure following combustion would just keep it closed. This valve was mechanically operated, and, in the case of the inline engine at least, it used a component that we haven't discussed yet, which is the camshaft. This was a shaft that has some specially shaped eccentric projections on it, which are known as cams, or sometimes lobes. As the shaft turns, the lobes push against mechanical parts, such as a rocker arm or a tappet, and this allows the valve to open and close. The camshaft is driven by a gear, or gears, that are connected to the crankshaft. Because it's connected to the crankshaft, it can precisely time when the exhaust valve is opened, and this dramatically increases the engine's efficiency. For all its benefits though, the Otto internal combustion engine does introduce a new challenge, and it's a big one. And that challenge is the simple case of cooling. Because we've switched to internal combustion, we now have an extraordinary amount of heat being generated by burning the fuel inside the cylinder. The combustion temperatures can exceed 2,500 degrees Celsius, or something like 4,300 Fahrenheit. Hot. The more RPMs your engine is generating, the more combustion is happening in a short period of time. That means your heat will be building up incredibly quickly, because engines are made from metal. Metal is a very good heat conductor. If this heat is not dispersed, bad things happen. Engine parts will warp, you'll have damaged materials, and if an engine runs too hot, the fuel-air mixture can ignite instantly in something that is known as a detonation. You do not want that. A lot of people might think that an internal combustion engine works by the fuel detonating inside. No, it is combusting. Combusting is not detonation. Combustion good, detonation bad. Detonation gives you broken engines, and possibly an exploding plane. Efficient cooling is equally as important as an efficient power-to-weight ratio, and it is a challenge that still dominates engine development to this very day. But for the purpose of this video, that's all the extra stuff we sort of need to know for the time being. I'll do other videos where I'll go into more details on how the Otto cycle aero engine works. I'll do videos that'll focus on the fun challenges of heat management, and others that break down the importance of certain key components, how they work, their development history, etc. So, returning to the engines. Not much is known about the one that powered Wolfert's first airship. We know it generated around 2 horsepower, but we don't know how much it weighed. As it was based on the original grandfather clock engine, we can assume a similar weight of around 50 kilos. And if we assume that, we get a power-to-weight ratio of 0.04 horsepower per kilo, which isn't particularly good. But as it was powering an airship, this wasn't as much of an issue. The important thing was the relatively high RPMs that the engine was able to generate, which produced enough torque to drive a simple air screw. With that, the airship was able to complete a 4-kilometer flight, which took off from Daimler's factory on the 10th of August in 1888. Over the following months, the airship continued to make successful short flights, including one that apparently took up Daimler himself, but the engine lacked power and it didn't have much endurance. A more powerful Daimler engine, this time a 2-cylinder, 7-horsepower model, would power another one of Wolfert's airships later on, but it would also be his last airship. The airship Deutschland first flew in 1896. It was the second of Wolfert's airships to bear this name, because the first one had gone up in flames 2 years earlier. This might have served as a warning for Wolfert, but he chose to ignore it. However, the first flight was a success, and over the course of 6 more subsequent flights, the airship managed to average a speed of 28 kilometers per hour. Unfortunately, on the 8th and final flight at 600 meters, the airship caught fire, and Wolfert and an engineer he was carrying up as a passenger were both killed as the whole thing came crashing to the ground in a blazing fireball. The cause of the fire was likely the hot tube ignition system that the early Daimler engines used. Wolfert had been warned about this, as it was considered a very risky combination to use something that required an open flame for heat generation with a giant airship that was filled with very explosive hydrogen. Many early internal combustion engines used this type of ignition system, which probably explains why a lot of airships didn't touch them for a while. However, the Otto internal combustion engine would see gradual improvement between the years of 1890 and 1903, and a pair of 4-cylinder 15-horsepower Daimler engines would successfully power the world's first rigid airship, the Zeppelin LZ-1 in 1900. This engine was a much more advanced design, and it made use of electric ignition, so no more risk of fire, explosion, scream and death. But they were still mostly unsuitable for heavier-than-air flight at this stage. The power-to-weight ratio of these engines was still subpar, but more importantly, the engines just needed to generate a lot more power overall. And the best way to get more power was to increase RPM. This breakthrough would come through a French car manufacturer by the name of de Dion-Bouton. The company was named after its founders. You had Georges Bouton, a toy maker and a gifted engineer, and the Marquis Jules Albert de Dion. Now, he was a classic turn-of-the-century French aristocrat. He was stupidly rich, he had a stylish moustache, and he had a habit of dueling anyone who vaguely insulted him. There was also a third founder, another engineer by the name of Charles Trépadu. He was Bouton's brother-in-law, and the original company name was named after him. But he threw a tantrum when the other two abandoned steam engines in favour of internal combustion engines and resigned. Before he resigned though, he did help develop the de Dion-Bouton engine. Now before you all start cooing and go, "Oh, look at the dinky little French engine," don't let the looks deceive you. This thing was quite revolutionary for its time. It was introduced in 1895 for the installation on powered tricycles, and it was considered the first truly high-speed gasoline engine. For comparison, early Otto engines ran at a speed of between 600 to maybe 750 RPM at a stretch. The de Dion engines achieved 1800 RPM as standard, and they reached as high as 4000 RPM in testing. The primary innovation that allowed the de Dion engines to reach such high speeds was it was the first successful application of timed electrical ignition. With hot tube ignition, the timing of combustion within the chamber was impossible. The fuel-air mixture would just ignite the moment that it reached a certain temperature during the compression stage. This was very inefficient because you're not extracting the most energy from the fuel-air mix, and it also required a really heavy flywheel to smooth out the inevitably uneven power strokes. This kept the engine heavy, and it kept the overall RPMs quite low. The de Dion-Bouton engine got around this by using a spark as an ignition source, and because a spark is electrically generated, it can of course be timed. This initially took advantage of an existing component that can be found in an Otto cycle engine, and that is the camshaft. The spark was generated by something called a make and break system. This involves connecting a battery to a circuit and then breaking that circuit. It was advantageous because the generation of spark using a make and break system requires a very low voltage compared to your spark plugs. Part of the circuit would be made up of two electrical contacts that were installed inside the cylinder itself. One of these was connected to the camshaft, which, through rotation, could cause the circuit to break by the contacts moving apart and therefore generating a spark and triggering ignition. Though it was effective, this system was very quickly replaced because it required complex mechanical linkages to pass straight through a gas-tight hole in the cylinder wall, which was difficult to maintain as the engine pressure increased. In its place, de Dion-Bouton used another innovative system that had just been adapted for use on combustion engines as well, and that was the magneto and spark plug system. The magneto is essentially a compact generator that's driven by the engine itself, and it was used to generate the high voltage current that was needed for a spark plug to work. Unlike the make and break system, the magneto system was not timed by the camshaft. It was a self-contained accessory, but the operation of that really is a topic for another video. All we need to know is that it worked. With the magneto, the de Dion-Bouton engine now had a reliable, timed electrical ignition. With an electrical ignition, you always knew when the power stroke was coming. Because of that, you could build your engine to run faster. Because of that, you could get away with having a smaller flywheel, and eventually no flywheel at all. This saved weight, and of course increased the power-to-weight ratio. The single-cylinder de Dion-Bouton engines were tiny. The most powerful model of them only ever generated around 8 horsepower. But because of their size, they could be air-cooled, and they were very reliable, and they proved, above all else, that building a high RPM engine was perfectly viable. At least one of them even flew. In 1898, one of the single-cylinder engines powered the first airship of Brazilian engineer Alberto Santos Dumont. He, of course, became a lot more famous 8 years later when he completed the first witnessed and certified heavier-than-air flight in Europe in 1906. This was with his flying machine, the Santos Dumont 14 Bis. Funnily enough, that flying machine was not powered by the de Dion-Bouton engine. It was powered by the Antoinette 8V, one of our baseline engines that we've already talked about briefly. The de Dion-Bouton engines were good, but they did not scale up well, and de Dion, for the time being, didn't pursue any further developments of that particular engine, or many other engines in general. They got a bit busy building cars instead. Other engineers, meanwhile, were pressing on, and the gradual iterative development of the aero engine slowly continued. By the turn of the century, engines were finally becoming light enough and powerful enough that they could be considered useful for heavier-than-air flight. But so far, all of the engines used in these attempts were engines that were being designed for use in vehicles. No one had yet designed an internal combustion engine for aviation from the outset. But that changed at the very end of the 1800s. It began with a new type of engine, the rotary engine. Now, to clarify, the first dedicated aero engine was not a rotary engine, but it did evolve from one. The concept had been kicking around in the minds of a few different engineers for the better part of 3 decades, but there was no effective rotary engine developed until 1899. Compared to the previous engines we've discussed so far in this video, the most obvious difference is the cylinder arrangement. They are in a radial pattern, but the differences go far beyond that. Indeed, if you want to be a bit crude with your comparisons, you could even say that the rotary engine is the inverse of the inline engine in both function and form. In the other piston engines we've looked at so far, the engine itself is stationary and the pistons are turning the crankshaft. But in a rotary engine, the crankshaft is stationary and the whole bloody engine rotates around it. This of course necessitates some fairly major changes to the internal design and configuration of its internal components. Because all of the cylinders are on the same plane, the connecting rods can't all connect to the crankshaft, they just won't fit. Instead, the pistons use something that is known as a master and articulating rod assembly, sometimes known as a master and link or maybe a master and slave assembly depending on where in the world you're from. One piston has the master rod, and that is directly attached to the crankshaft. The other pistons are then connected to attachment points that are around the end of the master rod where it's attached to the crankshaft. Another difference you'll find with a radial arrangement is that there is no camshaft. Instead, you have something called a cam ring or a cam drum. Now, if you look inside some more complex radial or rotary engines, you get this intimidating sight, which frankly makes you think, where the hell do we even start? And the good news is we're not going to start with any of it. The only thing we need to really know today is the basic detail of the cam ring, and it is essentially a big piece that sits in the periphery of the inside of this mess of beautiful clockwork. The inner surface of the cam ring has got lots of teeth because it is attached to a reduction gear so that it rotates at a fraction of the engine speed. Now, depending on if the engine is a rotary or a fixed radial, which we will get to soon, this works slightly differently, but the end result is the same. The rotation speed of the cam ring is very important because this is what will time the exhaust valves. On the outside of the cam ring, you see these sort of bumps. As the ring rotates, these bumps or lobes push against tappets or cam followers that drive push rods which are connected to the exhaust valves. There's obviously a lot more to explain, and there are more differences between inline and radial engines than that, but they will be getting covered in a separate video later on, as I am determined to not let the development history topic of this video get sidelined too much by mechanical explanations. The first successful rotary engine was built by Stephen Balzer, who was a Hungarian-born American mechanic living in New York. The rotary engine was an ingenious way of overcoming some of the limitations of contemporary internal combustion engines of the time. Firstly, they were an air-cooled engine that made excellent use of self-cooling, owing to the fact that the whole thing rotates. This means you don't need to worry about heavy and often temperamental water cooling systems, and the design also removed another major drawback of the low RPM engine, which was the reliance on a flywheel. By spinning, the cylinders acted as their own flywheel. Another distinctive feature of the rotary and the radial engine is that all of the cylinders are arranged in groupings of odd numbers. So you've got a 3-cylinder engine, or a 5-cylinder, or a 7-cylinder, or a 9, etc. This is because they don't go through power strokes sequentially. Instead, when the engine is running, every other cylinder is firing. This ensures that by the time the engine has completed 2 full rotations, every cylinder has fired exactly once in a perfectly balanced rhythm. Because of this, the rotary engines were among the smoothest running engines of their time, and this was further aided by the fact that the rotary engine specifically, relative to the mounting point at least, had no reciprocating parts. The pistons don't come to a stop at the beginning and end of each power stroke, because the whole cylinder arrangement is orbiting around a stationary crank pin. It's always in motion. There's never a start-stop. There's just a constant, smooth rotation. Balzer built 2 engines towards the end of the 1800s. He built a 3-cylinder one and then a 5-cylinder one, with the intention of installing them in early cars. But his efforts attracted the attention of one Professor Samuel P. Langley, who was perhaps the best financed person in aeronautics in the world at the time. He'd successfully tested a steam-powered flying machine that he called an aerodrome, And it was so impressive that he'd been commissioned by the government to build a larger one that could carry a man and become the first man-carrying, powered, controllable, heavier-than-air flying machine. No pressure. Langley knew that a steam-powered engine wasn't going to cut it, so he approached Balzer and asked him to build him an engine for the aerodrome. Unfortunately, like many other designers of his time, Balzer would struggle to scale up his engine for Langley's needs. Balzer didn't give up though. Indeed, he was incredibly stubborn when it came to designing something that worked. He continued to try and refine his engine's design, and eventually got to the point where his 5-cylinder engine could deliver approximately 8 to 10 horsepower, but it still wasn't enough. Refusing to accept defeat, Balzer would continue to work on this engine until he was literally forced to stop by running out of money and going bankrupt. Professor Langley failed to find a suitable replacement. He couldn't find anything that was light enough and with enough power on either side of the Atlantic. And eventually, it was up to his assistant, Charles Manly, to come to the rescue. Manly initially thought that Balzer's engine could still work and he just needed to tweak it to get everything working perfectly. But every engineer he spoke to essentially told him that the rotary engine was a dead-end concept and it was never going to be a success. After hearing this response again and again and again, Manly eventually despaired and decided that he would work on a new design. Sort of. He pulled one of Balzer's original engines apart and rebuilt it into something that was so different that it might as well have been a brand new design. Instead of an air-cooled 5-cylinder rotary, he now had a water-cooled 5-cylinder static radial. The rotary and the radial often get confused, and that's because they have some similarities. Both have cylinders arranged radially around a drum-like crankcase. Both have odd numbers of cylinders. Both fire their cylinders in a 1, 3, 5, 2, 4, etc. pattern. And both make use of something like a master and link conrod system. But unlike a rotary engine, which is built backward compared to your traditional inline piston engine, a static radial engine still functions like a normal inline piston engine would. It has a stationary engine block and cylinders, and a crankshaft that rotates. But why did Manly change to the static radial? The main issue that dogged Balzer's development of his engine was that he could not improve its cooling. Advances in machining would, in the not too distant future, yield air-cooled designs that could manage this, but for the time being, the air-cooled option was not really going to work. So instead, Manly decided to weld some jackets around each cylinder and fill them with water, making it a simple water-cooled radial. This primitive system worked, and it allowed him to bump up the RPMs, and he got the output of the engine to be between 12 to 16 horsepower. Encouraged by this, he then took the concept and designed a whole new, larger engine based on his Frankenstein's rotary. The result was the first engine that was designed from the drawing board to be used on an aircraft first. It was built in 1901 and eventually known as the Manly Balzer engine, although for a time Manly was a bit naughty and tried to claim all the credit for himself. This engine has been rightly called by many people something of a masterpiece, because even just in terms of pure power output, this thing was years ahead of its time. It produced 52 horsepower and had a dry weight of just 62 kilos, which gave it a power-to-weight ratio of 0.83 horsepower per kilogram. This was the first internal combustion engine to beat out the most efficient steam engines in this category. Now, the reason why this engine was so powerful is because it was a labour of love and dedication. No manufacturers could guarantee the precision build quality that Manly and his team were requiring of it, so they just decided to do the whole thing themselves, more or less. They designed and built all of the auxiliaries and the accessories, including the water pump, the spark plugs, and the propeller drive. The cylinders were constructed from spun steel shells that were only 1.6 millimeters thick. Manly then successfully shrank cast iron liners of the same thinness into these shells to ensure proper lubrication, a feat of engineering that many experts of the era had told him would be impossible. The result was not only a very powerful and light engine, but one that, for its time, was insanely reliable. This thing ran at full throttle for up to 10 hours, and as far as I'm aware, nothing else beats it in this category for several years. Now admittedly, it did help that it was able to run this long because it ran at a relatively low 950 RPM compared to the, 1800 of the smaller de Dion Bouton engines. But that lower RPM makes it all the more impressive that it could still generate 52 horsepower. Indeed, from a power-to-weight ratio perspective, this engine wouldn't be surpassed for over a decade. Unfortunately, it was a brilliant engine that was installed on an unsuccessful flying machine, which is ironic as the world's first successful manned heavier-than-air flying machine was powered by a much less powerful and technically less advanced engine. The engine in the Wright Flyer was, though, still a purpose-built aero engine, so it's worth mentioning it still. The Wright engine put aside the delusions of grandeur that the Manly Balzer engine has, and goes for good old-fashioned reliability and simplicity. It was a modest 4-cylinder inline that was arranged horizontally, so it basically looks like it's lying on its side. It was interesting because it had not one, but 2 chain-driven camshafts. One controlled the exhaust valves, like on a normal Otto engine, and the other was connected to an old-school make-and-break electrical ignition system. It produced 16 horsepower when it was initially fired up, but this dropped down to about 12 horsepower after a minute or so when the engine had warmed up, because the air intake metal would warm up, which would expand the hot air going into it, which means you have less air going into the cylinders, so less power. The engine only had a power-to-weight ratio of 0.17 horsepower a kilo, which is less than a quarter of that of the Manly Balzer engine, but it was more than enough. Unlike most of the other aeronautical pioneers, the Wright brothers had focused a lot of their time on learning to walk before they could run, when it came to designing an aircraft anyway. Because the Wright brothers had spent so much time focusing on understanding and mastering aerodynamics and flight control with various gliders before moving on to powered flight, the Wright Flyer was very aerodynamically efficient. It didn't need a powerful engine, and because it didn't need a powerful engine, the engine didn't need to be particularly advanced and they could just focus more so on reliability. The engine didn't even have a carburetor, for goodness sake. The gasoline was just dripped onto the hot water jackets surrounding the cylinders, where it evaporated and was then sucked into the intake ports by the vacuum created by the pistons. The internal combustion engine had finally achieved successful, powered, manned, heavier-than-air flight. But to make the flying machine practical, the engine would need to continue to improve. It would need to become more powerful, more efficient, more reliable, and more available. But in 1903, engine development was still in its infancy, and the aero engine industry still didn't exist yet. But by 1906, this had finally begun to change. The Antoinette 8V would become the first aero engine to put into production and sold to customers, and it powered the first significant heavier-than-air flights in Europe. Although it was designed initially as an engine to be put into cars, the Antoinette 8V was innovative as an aero engine for a couple of reasons. Firstly, it had the first successful application of a manifold fuel injector. This was a device that sprayed a fine fuel mixture into the airflow instead of relying on a venturi like the carburetor did. However, the fuel injector didn't catch on, at least not yet anyway. It was more complex, it was more expensive, and at the time it offered no performance advantage over the carburetor, and it would remain an outlier in aero engine design for at least the next few decades. More importantly, the Antoinette 8V was innovative because it was the first successful application of a large and practically useful V-engine in an aircraft. As the name might suggest, this is an engine where the cylinders are arranged in 2 rows, or banks, which are both mounted on a single crankcase, and they are driven by a common crankshaft, and because of the angle they are arranged in, they make the shape of a V when you look at it from the front, hence V-engine. A key feature of the V-engine, other than the V shape, is how the rods from both sides of the V share the same crankshaft, because when you think about it, there'd be a bit of a physical conflict. Historically, this has been handled in a couple of different ways. You've got the side-by-side configuration. In this, the cylinder banks are slightly offset so that the rods from each side can sit next to each other on the crankshaft using a single crank pin. You've also got something called the fork and blade, which is a little bit more different, where one rod is essentially forked at the bottom and it straddles an inner, thinner section, or known as the blade, on the rod from the opposite cylinder. And then you have the master and link arrangement, which is similar to what you would find on a rotary or on a static radial engine, where you have a master rod and a linked rod. V engines became attractive because of the fact that when you use two banks of cylinders on a single shaft, you provide more frequent power strokes per revolution than on a single row. This results in a smoother flow of torque, and it helps to eliminate certain types of vibrations, and it means you can, in some cases, do away with the flywheel altogether at this point. Indeed, it's around this time that the flywheel really begins to disappear, not just because on rotary engines you don't need one, but with powered flight now proven, people are essentially using the propeller as the flywheel, because it's still a decent chunk of mass that's attached to the front of the engine. Surely the mass of that and the inertia should carry it through. And it turns out it does. Although V engines would go on to become very popular, in the beginning many of them struggled. Most early V engines were liquid-cooled, and this involved a complex system of radiators, pumps, and piping. It was basically a bunch of plumbing. And plumbing plus vibrations plus flying equals flying unreliable plumbing. And many early engine failures were traced to leaks of said plumbing. Pioneers like Glenn Curtiss would begin improving upon the V engine, and this was later taken up by manufacturers like Renault, Hispano-Suiza, and Rolls-Royce, to name a few. But for the time being, the single-bank inline engine would remain the more popular type before the outbreak of the First World War. It's now that we get to the point where the development of aero engines finally begins to accelerate. Between 1906 and 1910, the popularity of aviation exploded. Pioneering and long-distance flights began to prove that the aircraft was a practical machine, and it also highlighted the growing need, nay, the demand, for reliability. A brilliant example of this is Blériot's famous Channel crossing, because it nearly ended in disaster. His monoplane was powered by a small 3-cylinder Anzani engine, which was a static radial that had a W configuration, where the cylinders were up in a W shape, as you can see here. Blériot had selected it because it was a compact engine that had a pretty good power-to-weight ratio, but what he didn't realize was how appallingly bad its cooling was. During the crossing, the engine warmed up and then began to overheat. If it wasn't for a providential rain shower, which cooled off the engine enough for him to complete the crossing, Blériot would have wound up in the drink, and he could have drowned for all we know. But Blériot survived, and the Channel was conquered. This pioneering event, and its near disaster, added a huge amount of momentum to the continuing growing pace of aero engine development. And it was also helped by the fact that there was actually now possibly a profit to be had. Aircraft were becoming attractions all over the world. Aviators were the rock stars of their age, and there was even now some growing military interest in the aeroplane. Not only were aero engines beginning to be developed for sale to paying customers, but they were being advertised with posters, and you were now seeing the development of standardized parts and components. By 1910, inline engines, V engines, and radials had all successfully flown in numerous flying machines, and many were now being sold commercially. Some of these engines enjoyed more of a regional popularity, like with the inline engine, which was almost exclusively popular in Germany above all others. But none of these would match the popularity of the one engine that dominated the world before the First World War. It was the French-built Gnome 7, also known as the Gnome Omega, and it was a rotary engine. In fact, It was the first successful rotary engine to fly, and it somehow became the most successful aero engine in the world for years. It was designed by three brothers. They were Louis, Laurent, and Augustin Segon. Their engine was unveiled in Paris in 1908. It was a 7-cylinder air-cooled rotary. It weighed approximately 75 kilos, and it produced 50 horsepower at 1200 RPM. The brothers had gone with the rotary because of its inherent advantages, the weight saving of the rotating action of the cylinders and its active cooling, and they built the engine for strength and simplicity. They used the highest strength materials then available, which was an advanced nickel-steel alloy, and they kept the weight down by machining the cooling fins from a solid piece of metal. Through something not far removed from a mechanical miracle, the brothers got their concept so right that the first engine ran flawlessly, and it ran so well that it survived for years and years and years, and indeed you can still find it today at the Smithsonian. The Gnome 7 rotary finally provided the reliable and lightweight power plant that early aviators had been desperately searching for. The engine gained international fame at the 1909 Rheims Air Race, when Henri Farman had swapped out his unreliable Belgian engine at the last minute for a Gnome rotary, and subsequently won several major prizes. Following this, the Gnome rotary took the world of aviation by storm. 35 were sold in 1909, 400 were sold in 1910, 800 were sold in 1911, 1,000 were sold in 1912, and 1,400 were sold in 1913. By that year, production of the Gnome rotary exceeded the combined total production of every other engine manufactured in the world up until that point, and the design was soon being exported to every single country that could build an aircraft. Ultimately, the Gnome was so successful that it basically became the ancestor to nearly all other subsequent rotary designs that would enter mainline production. But putting aside the astounding success of the Gnome rotary, by 1910, the basic engine templates had finally been established. You had your inline engines, you had your V-types, you had your radials, and you had your rotaries. But already there was a growing list of offshoots and subtypes that were beginning to emerge. And the aero industry would expand and diversify massively between the years of 1910 and 1918. And, of course, much of this expansion and diversification would be triggered by a global and industrialized conflict. In less than a decade, the entire aero engine industry would transform and evolve on a truly massive scale, and the engines of 1918 would make the Gnome 7 rotary look like a little toy in comparison. But the rapid development of those engines will have to be another story for another day. Especially because I'm recording this at 2 AM in the morning. As always, thank you all so much for watching. And a big thank you, of course, to the Patreon supporters and YouTube members whose wondrous support helps to keep this channel going. So this was my first unscripted video, or at least 80% unscripted, I should say. I still use bullet points and prompting images, but this is part of a change that I've been wanting to implement for a while to A, make the video sound a bit more human and slightly less monotonous, and B, actually make it easier for me to record, because reading a script verbatim and speaking it and making it sound good is incredibly challenging, and switching over to this bullet point format has made things a lot easier. It does technically make the videos a bit longer in production time, because I essentially write the full script first and then convert it into bullet points, but hopefully I can streamline the process a bit as I get used to it. A big thank you, of course, to our Wing Commander tier supporters, our highest tier members, and a warm welcome to Andy Johnson, who is the newest member of this special group. You'll be happy to hear that there are more videos on the way that will cover other various engineering topics, but I'm not going to neglect aircraft either. And to answer the constant question of when are you going to cover jets, it's happening very soon. Just the first jet videos that I've been planning have taken a lot longer than I thought would take to actually get finished. But as a brief spoiler for people, one of my first major jet videos will be on the de Havilland Comet airliner, so hopefully that is something to look forward to. That should be coming out within the next couple of weeks, along with the first part of a multi-video series that goes into jet engine technology. So, hey, jet stuff is coming soon. But anyway, that is all for today. Thank you all so much, as always, for your wonderful support, and I will catch you all next time. Goodbye.